Good afternoon, everyone. I'm going to tell you how to create a password vault that cannot be cracked offline. So nowadays, users has numerous online accounts, and remembering all the passwords for each of the accounts is a serious burden. That's why experts suggest using password vault. So our user can collect all of our passwords in a vault and encrypt it using a master password. The vault service also allows the encrypted vault to be stored in a cloud storage, so that from now on, she only needs to remember the master password, and she can access all of her accounts from all of her devices. There are tons of password managers or password vault services out there in the market, and this shows that there is increasing popularity of usage of password vaults. And this also raises the question, how secure is our password vaults? So the specific threat model that we are considering is, what if an attacker gets hold of the vault ciphertext? The attacker can obtain this ciphertext either by compromising the server where the vault is synced, or by exfiltrating from the user's machine. So apparently, it feels that, OK, the vault is encrypted, so the attacker should not learn what is the valuable data inside it. But what the attacker can do, he can mount an offline brute force attack against the vault. So he will try to decrypt the vault using his bunch of master password guesses. And the way normal traditional encryption scheme works, the output of the decryption will be either failure or a junk if the guess is wrong. And the moment he is able to guess the correct master password, the decryption will output a legitimate plain text, which is very easy to say that, OK, I have got the correct master password, and this is the password vault. So the total runtime of the work, that the total computational effort of the attacker is the number of decryption attempts. We call this offline work because the attacker doesn't need to go contact any server. Now the question is, how easy to guess my master password? OK, so the studies shows that 70% of the human-chosen passwords can be cracked less than 1 billion attempts. OK, and the bottom line is, if you lose your vault today, most likely your vault going to be cracked by tomorrow. So what we are trying to achieve, that how can you stop the attacker from cracking the vault offline? And the way we will achieve this by using decoy techniques. This idea was first introduced by Buzhinov, Bernstein, Bowen, and Bonnet. They proposed a new vault service called camouflage. Our first contributions will be to show that camouflage may degrade the security in many important cases. We'll move on, and we'll propose a new mechanism called natural language encoder, and thereby using honey encryption on top of password vaults and make it uncrackable offline. We'll create a full vault service using this honey encryption and natural language encoder. We call it no crack. So first, we'll describe what is the problem with camouflage, how camouflage works. So camouflage is a pretty nice trick. So they not only encrypt the normal vault, they create a bunch of decoy vaults and decoy master passwords, encrypt each of the vaults using the corresponding master password, and this whole list of they store a whole list of ciphertexts. So for our example, we have 3 decoy vaults. In real scenarios, it will be something like 1,000 or 10,000 decoy vaults. So when someone will try to decrypt a vault, the decryption will output 3 things. Either if your guessed master password is correct, it will output the real vault. If the guessed master password is one of the decoy master passwords, it will output a decoy vault. Or if your master password is neither the real nor the decoy, it will output a junk. So let's see what will happen if attacker try to brute force a camouflage vault. He will not only get a random junk, as before, he will also get some plausible looking vault and might be the real vault also. So at the end of the game, the attacker will get a bunch of plausible looking vaults, and he will have no idea which one of these is the real vault. So only option to check, and ideally to check the veracity of the vault, he has to go online and try to log in with the credentials inside the vault. And this will actually enforce that the attacker has to do all the offline work and then do some online work proportional to the number of decoy vaults created at the time of encryption. And the camouflage argues that, OK, no attack can do better than this naive attack. But we found a subtle vulnerability in the camouflage. And basically, the way they generate decoys is all the decoy passwords, especially the master password, share the same template as the original one. Like here, if the real master password is mypass4, all the decoy master password will also have 6 characters and followed by a digit. What the attacker can exploit this information in the following way. He will try to decrypt the camouflage vault as previously with his list of guesses. He will probably most likely get junk initially. But the moment he gets a plausible looking vault, he learns the structure of the master password. And now he can go online, check whether the vault is correct or not. If it is correct, he is done. If it is not, he can move on by pruning out a lot of the master password guesses that do not match this structure. And this actually, we found out that this actually gives a big speed up. We simulated the attack scenario using real passwords from the real leak. So for our test, for example, we use the camouflage where you use 10,000 decoys. And ideally, the attacker should do all the offline work and 500, at least at an average, 500 online queries. But what we found, the attacker can get to the real master password in half of the effort compared to normal password-based encryption schemes. And the online work is also negligible. He just needs only 11 online queries to find out whether the vault is real or not. So the situation is passwords are very easy to guess. And password-based encryption scheme cannot save our password vaults. The first approach in creating a decoy technique actually makes the security worse than the normal password-based encryption scheme. So we created, we now need to find out a better approach. And we were first motivated by honey encryption. Previously, Jikong gave a nice introduction of honey encryption. Let me remind you again. So the main idea is, if you try to decrypt the honey encrypted ciphertext with any key, it will output a plausible-looking plain text. And they achieve it by the following way. They encode the message to a bit string, and then encrypt the bit string to the ciphertext using any standard encryption scheme. The decryption works in a similar way. You decrypt the ciphertext to a bit string, and then decode the bit string to a plausible-looking message. And the good thing is, if you try to decrypt using a wrong key, the output of the decode will be another fresh random bit string, which the decode will convert that into another message, but which looks plausible. So in the whole setting, the most interesting and key challenging part of honey encryption is creating this encode and decode in a secure manner. Currently, in the previous work, we have encoder and decoder for relatively simple distributions. Recently, we also have encoder for genomic data. And we will show how to create this encoder for relatively complex distribution like natural languages such as passwords. We call these encoders as natural language encoder, which the functionality-wise, it takes a password and can encode it into a bit string, while the decode takes a bit string and convert that into a password. The main security criteria of this, that decoding a random bit string should look indistinguishable from a randomly sampled password. So the thing is, the main idea is that we need to have a good model of the password distributions. And the best part is that we already do that. The password crackers already tries to do that. So what happens is the modern password cracker, they try to learn a password model from a password leak, and then use that model to generate passwords in the decreasing order of their likelihood. To generate better cracker, the researchers always tries to create better models. And what we'll show that we can take this model and convert it into an NLE. In our paper, we have shown a bunch of generic a bunch of approaches how to convert these models into a secure NLE. Our approach is quite generic. And for example, like for n-gram Markov model, probabilistic context-free grammars, how can you convert those things into an NLE? Also, the password vault contains a bunch of repeated and related passwords. We also have a scheme to handle that situations. To give a high-level view, so we have seen how to do with the n-gram. It's more similar to the genomic that you just seen. For the PCFG, it's like you take a parse of the password and encode the password into a compact bit representation, while decoding will take a bit string and convert that into a parse tree and output the associated passwords. I'm glossing over a bunch of details that will make this NLE secure and usable. But the bottom line is, if you can make a better password model, we show how can you convert that model into a better NLE and thereby create better decoys. So we took this NLE and take the honey encryption and create a full vault system called NoCrack. The best part is that if you try to decrypt a NoCrack ciphertext with any master password, it will output a plausible-looking vault. NoCrack also supports machine-generated passwords and other functionalities like domain hiding, easy online sync, etc. Now we turn into how secure is our NoCrack, how better than the previous approaches. So we want that the output of the NoCrack decryption on a random master password should look like plausible. We come up with a bunch of attacks, and the best attack we could come up with using machine learning classifiers. And simulating on real passwords leaks, we found that if the attacker needs Q queries to decrypt a password offline, he will need at least Q by 3 online queries. He has to make at least Q by 3 online queries, which if you turn into a number, if for Yahoo leaks, if the attacker needs to break almost 87% of the password in 2.5 million guesses, he has to make 800,000 online queries, which is way more than any website will allow, and he will most likely get locked out. These all do not come without some limitations. The first limitation is the site information, that if the attacker has some side information about the victim, such as he knows one of the password of the victim, then it will be he can prune out the decoys and decrease his online queries. We also did not take into account the scenarios when the master password is related with the passwords inside the vault. Also, lots of websites enforce password policies, and our current NLE does not take into account that scenario. But we have some idea to implement it. We haven't thought through it. And finally, the attack that we have proposed is which shows our best effort, but we have no proof that there cannot exist some better attack against NoCrack. So we welcome the community to try find out better attacks against NoCrack. Said that, NoCrack never degrades the security relative to password-based encryption scheme. So even given these limitations, the attacker at least has to make all the offline brute force all the effort of a normal password-based encryption. So let me summarize. So we showed that the only prior approach on trying to deploy decoy techniques actually degrades security. We devised a new mechanism called natural language encoder that can encode natural languages to a bit string and thereby use honey encryption on top of it. And finally, using this NLE and honey encryption, we created a prototype of a password vault, and which we call NoCrack. Thanks for your attention. I'm ready to take your questions.
Thank you very much. So I did have one question. I think you might have touched on it related in the limitations, but I would imagine that there'd be a lot of coupling between individual passwords within a certain person's vault.
Yes, and we have that is NoCrack handles that, the interdependence of passwords inside a vault. but it doesn't do how master password is related to the password inside a vault.
Okay, cool. And then one final one. Did you do any sort of human-based evaluation of which ones of these like feasible versus which one of these are honey-based? I know that once you start working with these encoders, there might be a lot of inference at the human level that you wouldn't necessarily be able to build into a model.
I understand. So we didn't do it for two reasons. One was it's pretty slow, and it feels like machine learning, like it needs a lot of expertise to find human who can distinguish between this decoy and real passwords. Like someone has to look through those passwords and password leaks that what kind of passwords people generate. And mostly, like if you ask an individual password, he is biased to the kind of password he generates.
Right, right.
So it's we could not come up with a good like experiment scenarios how you can use human in this.
Yeah, I guess I wasn't worrying about a rigorous experiment as much as you probably looked at a lot of passwords over the course of working on this.
Yeah. So exactly. That's giving me the feel. Okay, I could not distinguish other humans.
Cool, cool. All right, let's thank the speaker one more time.